Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Don't forget to let us know what you like and stay connected. We love hearing from you. One of the biggest problems in spaceflight is the issue of power. Even if SpaceX gets us to Mars, how will we power our colonies on a planet with less than half the available solar power of Earth, and that suffers from planet-wide dust storms? The answer is, of course, nuclear power. We have discussed fusion reactors, but these are still on the horizon, though the MIT spark reactor is getting very close, and innovative aneutronic reactors may be possible soon. But these either have a lot of mass or don't have a high energy density. Energy density is measured in joules per kilogram. Let's put this in perspective. Here's a AA battery. It can produce about 15 joules per day for about 2 years, for a total of 10 kilojoules. Let's refresh our memory on what a joule is by reviewing some units important to space science. Kilogram is a unit of mass, whereas pound is a measure of weight. The imperial equivalent to a kilogram is called a slug. The metric equivalent to a pound is Newton, which is the best measure of force. We measure our starting mass in kilograms, then multiply by Earth's gravity to get weight, decide on our thrust-to-weight ratio, which, like many ratios, has no units, and get the thrust or force required to launch our rocket. The rocket will accelerate upward, burning propellant as it goes. The amount of burned propellant can be calculated in several ways, but usually we divide the thrust by the exhaust velocity of our rocket engine to get kilograms per second, usually denoted m dot, which is our mass propellant flow. So every second, our rocket loses mass, increasing our thrust-to-weight ratio. If we don't throttle the engines back, we might reach an acceleration that overstresses our rocket. As our rocket climbs and reaches a higher altitude, work has been done. Work is measured in units of joules, which is newtons times distance. This is also our measure of energy. These can be the same because they both measure the transfer or conversion of energy from one form to another. For the rocket, work is the transfer of energy that occurs when a force is applied to an object and moves it in the direction of force. In this case, chemical energy in the propellant tanks is converted to thermal energy, which is converted into the momentum of the exhaust, which is converted into the kinetic energy of the rocket, and the potential energy from its new altitude. Energy itself is the general ability of a system to do work. This energy can be kinetic, potential, thermal, chemical, or electric. Electrical energy is one of the most useful types of energy that humanity has discovered so far, and can be used to produce other types of energy. Chemical in the electrolysis of water, or kinetic in our electric cars, or even rocket thrust, like the electrothermal rocket engine seen here. These engines use electrical power from batteries and solar arrays, or potentially nuclear power, to heat or even ionize a propellant to produce thrust. These are different from ion engines that use magnetic or electric fields to throw the propellant out the back. Electrothermal engines use electrical energy to heat the propellant and allow its expansion to accelerate it. One of the best designs for this type of engine is the Variable Specific Impulse Rocket Engine, or VASIMR, designed by former astronaut Dr. Techziz, and described at length in this lesson. The VASIMR turns a gas into a plasma so it can be controlled and bottled by electromagnetic fields. Then it uses radio waves to heat the plasma to extreme temperatures that would surely destroy any material, allowing it to expand out the back and provide thrust. This engine can operate in a high-thrust, low-specific impulse mode, or a lower-thrust, high-specific impulse mode, making it a fantastic design, if we just had the power it needs to work, with a high enough energy density to be practical. Some companies like ThrustMe turn water into steam with electric heaters to provide thrust and reaction control systems. According to their datasheet on their water-based RCS system seen here, the specific impulse is not very high. But for an RCS system, it doesn't necessarily need to be. It just needs to be precise. You would also need to keep your water heated all the time to keep it from freezing in space, which I think is a drawback over other propellant choices. They also have iodine-based ion and Hall thrusters for better performance, but these usually don't have the thrust necessary for RCS. And here we see a microwave electrothermal rocket engine called an MET. METs turn electricity into microwave frequency photons and use those microwaves to heat the water to a much higher temperature. This is a lot like an arc jet, but it does not need an electrode, improving endurance and reliability. To make a microwave electrothermal rocket engine, you need to allow a gas to come into the heating chamber tangentially, creating a vortex effect and keeping the engine cool. For water, this could be done with sonic vaporizers or just heating it to steam temperatures. 100 Celsius is nothing to a rocket engine. The engine needs to be started at low pressure, which means low mass propellant flow, to create plasma, but once the plasma has formed, mass propellant flow can be increased to high pressure, increasing thrust. The drawback to all these designs is power. The energy density of solar is not very effective for high thrust propulsion until you get past the orbit of Venus. Nuclear reactors and thermoelectric generators are not very efficient and take up a lot of space and mass. Batteries, even lithium-ion, does not have enough energy density, and they still need to be charged. But what if we had a battery that could charge itself, with a potential energy density orders of magnitude better than any lithium-ion, and that didn't need to be recharged for decades? China has announced the sale of a battery like this by 2025. This is the BetaVolt BV100. BetaVolt has been researching advanced beta-electric batteries for over a decade. The BetaVolt BV100 is 15 by 15 by 5 millimeters and generates 100 microwatts of power at 3 volts. This won't be powering your smartphone anytime soon, but coupled with a capacitor, it might be perfect for an emergency locator beacon that would pulse a signal for at least 50 years. The Chinese device uses a radioactive isotope of nickel, nickel-63, that decays into copper when a neutron turns into a proton and a high-speed electron. The high-speed electrons can be harvested from this reaction using doped diamond layers and other materials in a structure called a Shockley diode that will absorb this electron and make it available to produce electrical energy. The University of Bristol is working on a design like this using carbon-14 that is even more efficient. All beta-voltaic batteries are limited in efficiency by the Shockley-Kessier limit, but this can be optimized using multi-layered tandem cells to about 33.9% efficiency, which has been reached by the Chinese manufacturer Longai in 2023. They are also looking at other isotopes like strontium-90 or promethium-147 as a beta source, meaning that we might be able to use nuclear waste to power our spaceships in the future. Beta-voltaic batteries have an energy density potential of 100 to 10,000 times that of our best lithium-ion batteries today. My question is this: what if we could make the structure of the ship itself out of carbon-14 fiber or nickel-63 or a combination of both, using nickel on the outside hull for radiation protection and carbon-14 fiber on the insides as well as the floors and walls for more power and to absorb secondary radiation, with a protective layer of water between us and the rather weak beta radiation. The dry mass of the SpaceX Starship is about 10% of its propellant mass, and should be able to lift up to 150 metric tons to low Earth orbit soon. Whether it and the booster survives the trip back down is not relevant to our discussion. Of our 150 metric tons, let's make about 15 of those tons dry mass. If the structural mass of the hull of our advanced beta-voltaic ship was 50% of the total dry mass, leaving an equal mass for pipes, cables, and other components, that would give us 7,500 kilograms of potential nickel-63 and carbon-14 mass. The best lithium-ion batteries today have an energy density of about 700 watt-hours per kilogram, with lithium oxygen having a theoretical limit of about 1,400 watt-hours per kilogram. But there is a lot of extra mass and support structures that we won't need in these batteries. Let's go with 1,000 watt-hours per kilogram and boost that by a factor of 1,000 for our beta-voltaics. More than 100 times the base for beta-voltaics, but only 10% of the 10,000 times limit. That would give us 1 megawatt-hour per kilogram for our nuclear battery spaceship. With 7,500 kilograms of beta-voltaic structure, we would get 7.5 gigawatt-hours of power. Now, nuclear batteries are different than regular batteries, as they recharge themselves through beta decay as they discharge energy, making more. If we could only harvest 1% of this potential energy. We could have a 150 metric ton spaceship producing 75 megawatts of power for half a century. With that much power, we could have very strong magnetic shields to protect us from galactic radiation, and extremely efficient and powerful ion and thermoelectric thrusters. A ship like this could go to the moon and take on a large mass of water for radiation shielding, oxygen production, and personal use, and then lift back off. Using an engine like the Vasimer, it could get us from Earth or lunar orbit to Mars in just 40 days instead of the usual 270, continuing to fly around the solar system for the next 50 years. Or we could make an uncrewed probe with a high-efficiency engine and send it on its way through interstellar space to Alpha Centauri. Something to think about. There are links to further readings in the description, and stay safe. At Astra Pro Terra.
Since the 1940s, the UK has run many nuclear reactors for research, military purposes, and electricity generation. These reactors all use uranium as fuel, housed inside of a core made out of graphite blocks. This graphite core assists in the nuclear fission process, enabling a controllable chain reaction which provides a constant source of heat. This heat is then used to turn water into steam, which in turn drives turbines to produce electricity. Nuclear power plants, though, invariably create nuclear waste, and therefore when any reactor is shut down, the waste must be safely stored and contained. We then simply have to wait for it to stop being radioactive. However, this takes thousands to millions of years, making it a long-term safety and financial commitment to maintain and monitor. Because of our use of graphite-moderated reactors, the UK has created almost 95,000 tons of radioactively contaminated graphite blocks. This graphite is just one form of carbon, a common and stable element, but having placed these blocks in a high radioactivity environment, some of the carbon is altered by the nuclear energy, turning it into the radioactive isotope carbon-14. The carbon-14 will eventually turn back into normal carbon once its extra energy decays away, but this is a lengthy process, and the radioactivity of carbon-14 halves once every 5,730 years. Recently, scientists from the University of Bristol's Cabot Institute have demonstrated that the radioactive carbon-14 is concentrated on the outside surfaces of our graphite blocks, meaning that it is possible to process them to remove a lot of this radioactivity. By heating them, much of the radioactive carbon is given off as a gas, which is then collected. The remaining graphite blocks are still radioactive, just less so, meaning that they're less of a problem and less of a cost to deal with. The radioactive carbon-14 in gas form can then be converted at low pressures and elevated temperatures to form a diamond, which is just another form of carbon. These small, man-made diamonds have a strange property in that they can generate an electrical current when placed within a radioactive field. Our diamonds, though, are made of radioactive carbon, and so are able to provide their own energy to generate a small electrical current. This gives us a nuclear-powered diamond battery. For this to be used safely, though, another non-radioactive diamond layer is formed around the radioactive diamond, completely absorbing all of the dangerous radiation and converting it into even more electricity, making it near 100% efficient. There are no moving parts, no emissions, and no maintenance, just direct electricity generation. And since diamond is the hardest substance known to man, no other material could easily offer any more protection to the radioactive carbon-14. On the outside, only a tiny amount of radiation can be detected, but this is less than what a single banana emits, making it perfectly safe to handle. As we mentioned, the radioactivity of carbon-14 halves every 5,730 years, meaning our diamond batteries have an incredible lifetime. They would only reach 50% power in the year 7746. These diamond batteries would therefore best be used in situations where it's not feasible to charge or replace conventional batteries, such as in satellites and space exploration, or use in implantable devices, such as pacemakers. In fact, there are so many possible applications that we're asking the public to make their own suggestions using the hashtag #DiamondBattery. The development of this new technology solves some of the problems of nuclear waste, clean electricity generation and battery life, truly taking us into the diamond age of power generation.
We have Dr. Mark Carter here from at Astra to talk to us about the Vasimir plasma propulsion engine. So thank you very much for coming.
I've been asked to stall just a little bit while we get organized, but I'm Mark Carter, and I'm a Vice President for Technology Development at Astra Rocket Company. So our flagship project really is the Vasimir engine that we're trying to develop. That's variable specific impulse magnetoplasma rocket that goes back a long time, actually, in terms of its idea. How you actually implement the idea has really come about because of RF radio frequency wave generation broadcast radio, basically tied into magnetized plasmas. So we're the most advanced high power electric rocket today, and when I mean high power, I mean more than 40 kilowatts. Below 40 kilowatts, you have better options in terms of mass from Hall thrusters and ion engines. Above 40 kilowatts, we scale very well with increasing power, because once you make the magnet, you can put more and more power through that magnet until you basically hit thermal limits. And so we can scale, we believe, all the way up to multi-megawatts. You see the same basic technologies being used in fusion experiments, in this country, although a lot of those are shutting down, but still in Europe for the large experiments in Europe for fusion, they run multi-megawatt systems, very similar wave physics involved. The design is electrodeless. Everything is done with electromagnetic coupling, so you don't have to separate the electrons and the ions to accelerate the ions. The waves, the natural waves that set up in the plasma, do that for you if you exploit the physics and the properties of it correctly. It's really doesn't care what propellant you use too much. We like to use noble gases just because they're easier in the lab to deal with, and things like argon are relatively abundant throughout well, certainly on Earth and at Mars and different places. And so that's what we've chosen. It provides a good specific impulse of around 4,000 to 5,000 seconds, which is kind of what you want for cislunar and Mars. And it's cheap. We have also the ability to adapt by making more plasma and accelerating more plasma with less energy in the booster section. It's a two-stage rocket. You can actually adjust the specific impulse with a fixed gas without having to change gas. And that gives you a little bit of range and specific impulse depending on what you want to do with your mission. So that's some of the advantages of this technology. So as I mentioned, these engines exploit the natural resonant modes in the plasma. So, and these modes we choose by design, actually. You want to, any electrical power source will work. We use DC input because we're gearing towards solar panels for the first power systems. And so we don't really care whether it's nuclear or solar or what the electric power source is, but it is electric rocket. Many types of propellants we've tested. We haven't tested actually iodine, but there's no reason why it shouldn't work. But we've tested all the rest of them in source and some with acceleration. The necessary technologies are already available. Radio frequency solid state amplifiers from broadcast radio now are most impressive, and what they can do even now with some of the newer generation of FETs is really incredible. You can get 95+% conversion efficiency to the waves that we want. So when you're tuned, everything is very efficient in taking the electrical power and getting it actually into the plasma. We do use superconducting magnets. We've been using them since 2010. It's different than most. It's similar to the MRI magnets that you see in the hospitals. It's just under 2 Tesla maximum field. And it is conduction cooled. It's not, it doesn't have liquid helium sloshing around it. It actually has cold heads that attach and conductively pull the power out, which is an important technology for space. You really don't want liquid helium running around, loose in your system. We have been looking at high temperature superconducting design since 2011. There's a company in New York called Superpower, Schenectady, New York, that have been building commercial versions of high temperature superconducting magnets. And that material's come a long way. It's now come down in price so that it's actually competitive, and we've got designs and plans to build them as soon as we can get funding for that. It's probably our next big push to get funding is for that magnet. And you can see down here at the bottom that we've been doing, from actually starting at Oak Ridge with some of the high performance computers here, we've been doing some types of plasma simulations showing how the waves are launched and propagate and absorb inside the plasma from the get-go. This is back to 2007, very early experiments we did in NASA. And here's the downstream end. We measured the performance of the plasma by passing targets through the system that have strain gauges, so we can measure the actual force locally and get spatial resolution for the profiles here too. So this we've advanced quite a bit. In the old days, we had these a little bit too close. If you leave them position fixed in fixed position, you'll burn up your probes. The heat flux coming out here is pretty impressive. And so we've moved to systems further back that's raster through, and they have time then to cool back off before they become obliterated. There's a picture of our vacuum chamber that we bought all with, this is all purchased with private funding, but you can see people standing here. This is Aiden and Matt working on the system. This is the control bank for currents through our superconducting magnet. We run about 40 amps through a little tiny wire. It's really pretty impressive how that works. You can see just a little bit of the plasma here in the background through this porthole. I've kind of covered it up with the words here, but this is part of a next step project with NASA. We've been doing it we're at the end of the 3rd year for this project and hoping to get advanced on to the 4th year support for that. We have completed 100 hours of operation with this system at 100 kilowatts. We didn't do it all continuously. There's a lot of facility issues. I didn't really respect how hard it was to do an experiment with 100 kilowatts inside a vacuum chamber. Everything that goes in has to come out. Plus, you have about 100 kilowatts driving the pumping systems for this system. So there's a lot of problems with leaks. You have, you can't really see, but right behind here is the manifolds that lead all the water cooling and systems that we have in there. We have run it with all those systems. We do run 50 kilowatts. We have run 50 kilowatts steady state. And we're fighting a little bit of a leak right now. We were supposed to be starting up, and we did start up last week to actually try to execute this 100-hour test. But we're going to have to pull it and fix that. It's really a seep. It's so small that it doesn't stop us at 50 or 70 kilowatts even. But to go to 100 kilowatts, it starts to make water plasmas. And so it's the leaks and seeps that actually get you, not the plasma physics and nothing else or like that. So the system really is full-blown TRL4 and getting very close to TRL5 by the time we get finished with these tests, which is the valley of death for developments. So we're always looking for money. We hope to get private funding, and we have a lot of private funding. This is about a $10 million investment from NASA, and as I say, we've raised about $30 million in private investment. We have new PPUs. Our PPUs are actually very simple systems compared to other electric propulsion systems because these waves basically are linear waves. There's some quasi-linear effects in that you get slow changes because of power and things like that, but you don't have any real instabilities that you have to fight like you have to fight when you separate the system out in what I would call an unnatural mode. Plasmas don't like to be separated. They like to stay, but they will jiggle and oscillate. And we have performance measurements that are better than 60% system-wide efficiency, and we believe we can improve that even further by going to things like the high-temperature superconducting magnet systems. The refrigerators are a lot smaller, and you have a lot less loss in the system. This is really a paradigm shift in how you would do space transportation, because everybody says high power. Well, what does high power mean? Some people would say 10 kilowatts is high power, and I would say no, that's not by our standards. We really are looking at 100 kilowatt systems, which are similar to what you use for transportation in your vehicle. I mean, we're human-sized creatures. We have to have human-sized things, and that means you're in 100 kilowatts for transportation systems. It's kind of amazing how that works. It doesn't matter whether you're on the freeway or in space. We are looking at commercial applications, everything from robotic to human transportation. Because we do scale to high power, we're of interest to human, but the money in the commercial side is much more on the cislunar and satellite servicing, things like that. So that's where most of our interest is actually for the commercial development. But we do enable pretty much exploration from low Earth all the way to Jupiter and even beyond. And so there are several interesting things that you can do. Here's just a brief technology development thing. It's been a slow slug going from a private company in 2005 all the way to where we are now. And we now have these designs that we're basically testing the components for in the system that we have now to go ahead and implement into a flight demonstration project, which we're hoping to fly something around 2022 if we can keep the funding rolling. We do have partnerships. We have this $10 million 3-year partnership with NASA Next Step, and we hope that can continue on. We're also working with a small company in Canada with the assistance of the Canadian Space Agency to develop these PPUs. They have industrial applications too, so they're developing them really as a product. Which we'll buy from them, and then the Canadian Space Agency will help us take it on to TRL-6. TRL-6 basically is where you start to fly, or you're ready to test your flight test. Northrop Grumman is also helping with a flight demo proposal, so we're looking at things like Espagrandes and things like that to fly on and integrate with. We'll be doing a solar-powered unit with battery backup, or basically battery energy storage, so that you can build up to your 150 kilowatt level, which we would like to test the engine at for a single string, discharge the batteries and then recharge them. So the solar arrays are still pretty expensive, but they do have these available. Orbital ATK, which Northrop Grumman purchased, actually has arrays that will go to that level. And there's also another company that develops arrays, and we don't really care what arrays we use, whichever package is the best, and we can afford to launch. Applications for the technology, space station reboost is something that we've been looking at for a long time. You have to basically keep lifted up, and we spend a lot of propellant right now trying to keep the space station reboosted, and you have to pay the Russians for that. So it'd be nice to be able to have this system which you could run, the argon supply would last a long, long time. And just solar power, you need about 50 to 80 kilowatts to basically boost and have good control over your you want to be able to boost and also maybe maintain 0G in different environments. And it wouldn't have to be for ISS. Anybody that has a space station will need to do something like this in lower orbit. Satellite servicing, I think we can do a lot with robotics. You can go move around. Plane changes and things like that are easy for electric propulsion compared to chemical. So you can do lots of applications that way. The space resources and mining, certainly going and getting an asteroid. We're the truck. If you want to go get an asteroid, we can help. At least we're the engine for the truck. The fast planetary human transport is what we're also interested in too, and the power scaling up to do that. So that's what I'm going to be talking about mostly here. So I think everybody in this room pretty much understands this, but the specific impulse of chemical rockets is just too low for deep space. They're great for getting off the ground, but their fuel requirements are very high if you just, and the capacity is very low. So here's your payload, and you even leave this, and this is the only thing you come back in going to the moon. So this is all fuel, this is more fuel, and here's more fuel so you can get back. So you can see how the stack up is really against you, and this is just going to the moon. You start going to Mars, and that's a much more difficult problem. And so an Apollo-style architecture for deep space just isn't sustainable. You could probably do it, but it's more like a stunt. If you want to really do it, you need an efficient and reusable architecture. And basically, energy is what drives the system. Physics requires energy to do anything in space. And so you can imagine this architecture, you launch to some sort of a transfer orbit. A tug would pick up your payload and carry it to the moon or orbit around the moon for whatever it's supposed to do. Or it could take it all the way to Mars, and you can then reuse this tug. So you bring the tug back, reload it, and hopefully you could make, dozens of trips to the moon, and at least, several, many trips. You can only do these trips to Mars about every 2.5 years, just on the synodic cycle. But you don't want to be restricted to closest approach and things like that. You want to be able to go every 2.5 years, no matter what the alignments are. And these types of tugs will allow you to do that. Taking large cargoes, you can actually amplify your payloads by a huge amount so that you can get very large cargo deliveries to Mars. They're fairly slow, but you can do that with solar power. If you just a little bit of interesting facts is that a 200 kilowatt solar array provides about 60 terajoules of energy in space over a 10-year lifetime. And so you can piggyback that and get that up with a medium lift launcher. It's easy to get in space by today's launch standards. 5,000 tons of chemical fuel with oxidizer provide about the same amount of total energy. So that gives you some kind of a clue about how much this power supply, in situ power supply for solar is worth. Nuclear energy, of course, is much more dense than chemical to the point where it doesn't really matter, but it really only helps you if you can reuse it. You really have to make sure that these systems are reusable, or else the cost is just going to drive you, you won't be able to sustain it. So reusability is a real big thing in this whole thing if we want to become sustainable. So a little bit about what humans would have to deal with going to Mars. First question is, how much risk are you willing to tolerate? You have a lot of complexity for mission assembly. You'd probably be assembling something close to lunar orbit so that you could take off there without having to fight the gravity wells. You have to worry about deep space radiation, and so you have time and shielding you can't do anything about distance because this stuff is coming from all over the place. But you have to worry about radiation if you're in space, especially deep space. The Apollo astronauts would see streaks through their eyes and things like that from galactic cosmic radiation and other things. They're pretty sure that's what it was. Or even protons for the sun can be a problem. So you really want to minimize the time you spend in travel before you get to some sort of shelter. You can carry some mass with you for shielding, but this type of radiation you're trying to shield against is very difficult to screen out. It takes a lot of mass to do that, and you don't really want to do that. So time is your friend here. Or it's your enemy. You want to make short time to solve the problem. Zero gravity is also a big problem. If you have enough equipment with you, you can sort of offset that. But if you go longer than about 6 months in space, it starts to cause a lot of problem. I've watched my neighbor who came back from the ISS after 6 months, and it took him 2 or 3 months before he could push his child in his stroller. So if you're going to get to Mars and land on the ground and be able to actually function, the gravity's lower there, but you're still going to have a hard time unless you get there, again, quickly and can maintain your health along the way. And we have sort of a fundamental thing. My boss is an astronaut. You saw him speak yesterday, but he really wants to come back. And I find that most astronauts would prefer to come back. Going a one-way trip is exciting for some people, but but man, it's just not something we want to do. So we always try to plan, on how you would return. And so what are your options for round trip? And you have several different things. You can integrate everything for the return trip at departure, which will be the way things probably are gone if you try to do it early before you build a lot of infrastructure around Mars. So this is something that's important to look at, and it's also relatively low risk because you integrate everything in a place where you can test it before you even leave. You could also pre-position your return propellant in Mars orbit or make it in situ, or however you do that. If you pre-position, you're going to have to take a lot of cargo ahead of time, and then you'll have a lot of added risk for assembly at Mars, which will have to be pretty much all robotic. I don't think you can, it's too slow a communication delay to do anything except that, really. Which means you need a bunch of satellite infrastructure and control stuff probably at Mars too before you can do that. Or you can get this propellant by in situ, but this is way on down the line before you'll have to have a lot of infrastructure in place. It's nice to have these lakes around here, but somebody had to build the dam before you could use the lake. And so I'm going to look a little bit at what technologies can improve the odds for this. And so NASA's already done a really nice job of what it really would take to get a habitat that people could live in for something like a 6-month period. It's this Design Reference Architecture 5. I'm not going to exactly follow their method for getting there, but they do specify a habitat would weigh about 65 tons. That's sort of the same size as a space shuttle type thing, something like that, which would give people enough room to have exercise equipment, be able to get away from each other. If you put too many people in too small of a place, they'll just kill each other. It's kind of a known fact. So you don't want that either. So I want to look at propulsion options that are TRL-4-ish or better. And so certainly we have LOX hydrogen engines. They are great systems. But they only have specific impulse of like 420 seconds. That's the number I'm going to be using in my slides. It doesn't make a lot of difference. It's low. You have NERVA 2-like propulsion systems that were developed for the Saturn upper stages. And they have specific impulse of about 850 seconds that maybe can go a little bit higher, but again, that's the ballpark. You can then switch to nuclear. I should say also solar here, but solar probably doesn't give you enough power to take people. So I'm looking really at nuclear electric. There you can get specific impulse ranges from 2,000 seconds up to 6,000 seconds or even higher if you need that. And you also want to look at aero capture. People are looking at aero capture a lot. It does help save. You don't have to have propellant because you have to stop. You can't just go and not stop. You just keep on going when you go to Mars. And so there's two fundamentally different things going on here. Okay. One is that LOX hydrogen and nuclear thermal are propellant intensive because they're low ISP. Nuclear electric and aero capture are plant intensive because you have to build the infrastructure into the rocket itself, and they use a lot less propellant, or effectively almost none. So you need to do fast travel times to Mars. Minimum energy transfers really don't count. So what I did was I just did a simple race. You basically just start and cover the radial distance between the orbits. It's about, on average, 77 million kilometers. You want to be able to do that every 2.5 years. Sometimes it's going to be faster when you're closer. Sometimes it's going to be, further when you're not lined up right. But you still want to have this sustainable cadence. And you just do a simple race. You accelerate, you coast, and then you decelerate, and then you carry enough stuff or have enough infrastructure to get back. And so you need to get there in less than 6 months. You can go look at things like assembly things. There's about a 92% chance, according to this paper, of successful integration for each launch with SLS at the moon. That can probably be improved and probably will be. That's a little bit older paper. But you assume that you position all this material in lunar orbit, and then you have different propulsive mechanisms for getting in, aero capture, or having your pre-positioned return stuff. And again, tugs can help with pre-positioning early on in the infrastructure. And what you find out is that NEP is fast for all the cases that I considered here. That's nuclear electric propulsion. The nuclear thermal propulsion is marginally fast if you have 5 kilometer per second aero capture. So here we have LOX hydrogen, which really can't get you back. It's marginal no matter what you have, so you really are colonizing here. If you go nuclear thermal, you can actually, if you add aero capture, can get close to 6 months, basically acceleration, deceleration times, one-way transits. But the nuclear electric gives you the ISP and gets you away from this. It gets you down the exponential in the rocket equation and allows you to go. And so I'm looking at, I think we saw yesterday somebody was mentioning, 10 kilogram per kilowatt was pretty straightforward. 4 kilogram per kilowatt is hard, but does gain you something for electric propulsion. And this is fairly realizable. Several people will say you can do this. This one is harder, but some people, I think Leonard yesterday said that he might even be able to do this or better. So this is not crazy if you actually go ahead and invest in the development for electric power plants. Plus you have a nice electric power source once you get there. It doesn't have to be used just for propulsion. And so if you do risk optimization and weight this thing by the extra risk you have to put in place by pre-positioning at Mars, this is you have to do this kind of crudely. So I did this just simply by how many extra launches you have to get to Mars. and you find that you really do win by going nuclear electric. And you also see the power sizes are not as big as you might think. When you optimize these times, it's very simple. You can go program this on an Excel spreadsheet. But you really want 100 to 200 megawatt thermal type reactors, which are good matches for 20% conversion efficiency to nuclear electric. So the same reactor might be able to be used for both very effectively. But they're not as big as NERVA. You don't want the full-size NERVA reactor. That's like having a giant dragster engine on your truck. You know, it just doesn't make a lot of sense altogether. And SEP cargo staging, I think, really is an important first step. You can do it saves a lot of costs going to the moon. So it saves staging costs. You could also then use this to get something like 30 tons to Mars every year based on SLS launches. So SEP, I think, is definitely a technology that's ready and ripe to be exploited. We just need the engines that can use that power, and it steps right on into the nuclear realm as you go. So I'm getting close to the hook here. Let's see, I guess the conclusions here, I don't have a lot of time, but you know, NEP is the only technology that really allows fast transits on a 2.5-year cadence. Aero capture will, if you do it propulsively, the lowest risk option. Aero capture definitely helps. It makes nuclear thermal become marginally fast, but it adds this critical maneuver on arrival. Aero capture is not easy. The prepositioned propellant requires a huge amount of infrastructure. You're going to have to already have cargo systems and other things in place before you can really start to do this type of work. And so it's nice to envision all this stuff and what you can do after it's there, but you've got to build that infrastructure to begin with. And solar electric cargo, I think, is really where we have to get started. And that's all I have.
This is the last image that I have for you, and it's a photograph taken by the Mars Curiosity rover from Mars, obviously, on a evening, clear evening sky. And that little tiny point of light is the Earth. That's where we all are. And the reason I close with that is because I figured that maybe someday, I don't know, amateur astronomer on Mars looking at the evening sky will take a picture of, look at that little point of light and tell, you know, his or her son or daughter, hey, you know, your great-grandfather came from there.